Hello out there everyone, and welcome to today's episode where we will be continuing our discussion on hydrology, and today we're going to be focused on the subject of hydrographs. So we will spend a little bit of time talking about hydrographs, how they're used, what some of their features are. We'll talk about different types of hydrographs. We'll look at an example of combined hydrographs, and then we'll follow up with an example problem of how to use a hydrograph to predict other types of storms. So, hydrograph characteristics. A hydrograph is a plot of the discharge flow rate over time from a watershed. So typically you would have a stream gauge in a receiving stream somewhere, and following a rain event, you'll get this peak curve of your discharge. So this is not necessarily directly related to your rainfall. You may have rainfall like this over time in your watershed, but as the rain drains from your watershed, depending on your time of concentration, you are going to have some increased flow rate up to your peak flow and then decreasing over time. So in this increasing side, we call this the rising limb, is typically what that's known as. And then you have your recession or falling limb on the backside, which does tend to sometimes kind of tail off. It's a little bit of a skewed distribution. And then at the top you have the crest, and the crest represents your peak flow rate. So under the curve, if you were to integrate this volume of area here is the volume, your total volume of runoff. So this is going to be like in millions of cubic feet or something like that, or typically in acre feet, or maybe kilometer meters or something. And so you can estimate your amount of volume by doing hourly integration manually. So for every hour of time, you basically use the discharge rates and the time, and you can just geometrically estimate what that area is and get a reasonable estimation of what your total volume would be. Now, these are specific to a watershed, the total rainfall for that rain event, and the storm duration. These are the three kind of factors that go into making a natural hydrograph. And a natural hydrograph is really just, exactly as we've described it. It's the plot of discharge over time, probably as measured in a stream gauge. However, there are other types of hydrographs, and one of the reasons we might use other hydrographs is to try to get away from some of these binding limitations, so that we can start using one hydrograph to predict a different storm event or possibly even a different watershed. And these can be used for watershed evaluations. A big one would be flood management planning. Knowing what kind of peak flow rate that you might be getting from a watershed is obviously very important for planning flood management. And also facility design for things like bioretention. You're going to need to know what the peak flow rates are going to be, or what the total volume is going to be, so that you can size them appropriately. And sometimes you may have a situation where you actually have kind of it's not necessarily zero if you have a stream, if you're gauging this from a stream, and the stream has perennial flow, then you may have to subtract out that base flow. And there's some different ways of doing that. The simplest is basically just a straight line where you just subtract that amount out from the initial time of the reading of the stream gauge at the initial time and after the storm event. Okay, so types of hydrographs. We already talked about the natural hydrograph. That's really just the simple, pure hydrograph that plots the stream flow or peak discharge over time, or discharge rate over time, I should say. There's a few others. There's the unit hydrograph that was developed in the early 30s. And these are really useful because that's how we can start predicting different storms of total precipitation. So in other words, like if we have a hydrograph for a 3-inch storm event, and which is really 3 inches of runoff. We'll talk a little bit more about the difference between precipitation and runoff in a minute, but we can use a unit hydrograph is really just the hydrograph for a 1-inch runoff event. And from that, we can scale that up to any other size. So if we want to know what a 6-inch event, what kind of peak flow or total volume it would have, we can do that from a unit hydrograph, as long as the storm durations are the same. That is kind of the catch with a unit hydrograph, because even if it's a 5-inch rain event, then, if it's 5 inches over an hour or 5 inches over 12 hours, these are going to have completely different peak flows, right? And really total volumes are going to decrease as you have a lower intensity, right? Because there's going to be more time to infiltrate the water into the ground. So there's something called the dimensional unit hydrograph, and this came out later in the 50s. Well, the standard came out in the 50s. So what this is it's kind of like normalized, I guess you could say. So the time, it's all a plot of the peak time. So if we were to talk about this point, this would be the time relative to the time to peak, right? Every point on here is time relative to time to peak. So that's why this is 1. And then on our y-axis, everything is discharge relative to peak discharge. So that's why this is 1, right? So everything is relative to the peak discharge and the time to peak discharge. And so these are used because they can get away from some of those issues of storm duration. And actually the NRCS has a standard unit hydrograph that was compiled from lots of different data, and they use this as sort of a standard that they can modify to particular basins. And then there's the synthetic hydrograph, which is actually doesn't use data at all, really. It's completely comprised of features of the watershed. So like land use, slope, soil characteristics. We can basically predict, without actual rain data, we try to predict how a hydrograph would look, or how a watershed would behave based on its characteristics, not in reference to actual storm characteristics. Okay, so you can also combine unit hydrographs. They're additive. So these hydrographs that we've been talking about are for what are termed regular shaped basins or watersheds. So either one of these, C1 or C2 here, either one of these could be considered a regular basin. So they're going to give hydrographs kind of like we had looked at. So we have one for C2. So now C2 has a lower time of concentration. And so when you have lower times of concentration, you wind up getting much sharper peaks, right? Because the water is going to concentrate together quicker and leave the system quicker, and you're going to have a higher flow rate because of that. Whether it's because, naturally the soils there's less vegetation, or they're more impervious soils, or there could be development in the watershed. And anytime you start, knocking down trees to put in parking lots or whatever, you're going to start having lower time of concentration. You're going to start shifting from this, which for this is a much longer time of concentration, right? So it's spread out more. You're going to start going in this direction. So that's a couple of things you can kind of tell just by looking at the shape of a hydrograph. Although in this case, we're more interested in adding these two together. So when you have watersheds like this that are both discharging, so this would be an irregular watershed, you can actually add the two regular watersheds together and get this kind of understanding that you're going to get this peak discharge and then kind of this a little bit of a second peak that trails off slowly over time. Okay, well, let's jump into our example problem. In this example, we are going to be solving for some characteristics of a unit hydrograph and then using that to try to predict this similar sort of characteristics of a different storm event, basically. So in this case, we're going to be looking at a 1.5 hour storm on a 2,000 acre watershed, which discharges to a receiving stream where a peak discharge rate of 800 cubic feet per second and a total runoff volume of 350 acre feet were recorded. We want to find the unit hydrograph peak discharge rate and the peak discharge and total runoff volume for a similar 1.5 hour storm. Now that's important that they match with 5 inches of excess precipitation. Okay, so that's not too difficult. We got a couple of different different problems to work through here. One, the unit hydrograph, and then using that in relation to this 5-inch storm event. Now we talked about 5 inch of excess precipitation, and I just want to quickly talk about what that means. So as we kind of mentioned earlier, this is not about the actual total rain depth, right? And typically people talk about a 3-inch rain event, 4-inch rain event. Well, but not all of that's going to become runoff, right? A 3-inch rain event doesn't mean you get 3 inches of runoff, right? You might get 2 inches or some other number depending on your watershed. So excess precipitation has to do with the precipitation that actually produced runoff, and it's expressed though in a depth like this. So what we first want to do, because we want to start trying to figure out what the unit hydrograph is going to be, we need to know what the excess precipitation is, because a unit hydrograph, remember, we want to figure out the hydrograph for 1 inch excess event. So we may have something like this, and if this is for, well, we don't know yet, but for whatever this is, the storm event we're about to solve for, we can get this for 1 inch unit hydrograph, right? And then, whoops, we can use that. Okay, we are back with a working pen again. Sorry about that. A little technical difficulty there. So we were talking about comparing these two hydrographs. So what we know about this hydrograph, this is our storm data that we have. We know the peak flow rate, right? That is our 800 cubic feet per second. And we also actually know the area under the curve, which would be 350 acre feet if we were to use those kinds of units. That's not necessarily as important, but what we do want to do is convert this over to a 1 inch unit hydrograph, and in order to do that, we need to know what is, we need to know what kind of storm event this is. And so we need to know what's the excess precipitation. Well, that's pretty easy to solve. Let me grab my notes. For this event, excess precipitation is going to be equal to the total volume of runoff for the storm event over the area of your watershed. So if you think about it, you're basically spreading the volume out in a relatively thin layer across the entire area of the watershed. That's the depth of the rain that became runoff. That's why we call it excess precipitation or net precipitation or runoff precipitation. These are different terms people use to describe the same thing. They're all a little bit poor of a choice in my opinion, but I'm going to stick with excess precipitation because that's what I'm using, writing it as PEX here. So that would be our 350 acre feet over our 2,000 acres. So units are quite convenient when you have them this way. Although we do need to, that would be express it in feet, right? But we want to express this in inches, since that's generally how hydrographs are done, either inches or centimeters. So this is going to be 2.1 inch, which means this would be for a 2.1 inch event. And once we have that, we can solve for our peak flow of the unit hydrograph quite easily. It's just going to be whatever it is for the information you have. In this case, we have it for 800 cubic feet per second. And then we're going to scale that. Now, I say scale because that's really what we're doing. We are not, obviously, feet and inches are not going to be directly compatible units, but we don't want to convert them because we're really only using 2.1 as a scalar. We just want to scale this down to 1 inch. So you might even say inch per inch or something like that. Actually, is probably better. So this becomes 381 cubic feet per second. That is going to be the discharge rate for our unit hydrograph. Now, the next couple of things we want to do, we want to find the peak flow rate and total volume for a similar duration 1.5 hour storm and 5 inches of net precipitation or excess precipitation. That's pretty simple. I guess, well, we can try to put some of it on here. So the first thing, we already know what it is for the unit hydrograph. That's the whole point of unit hydrographs. They make it really easy to figure this out for, if that's 2.1, this is going to be 5, right? Something like that. So our peak flow rate for a 5-inch storm, we just scale it again, right? So we have our 381 cubic feet per second times 5 inches. I'm going to say inches per inch. And if you include all the significant digits from the calculation, you're going to get 1904.8 cubic feet per second. And our volume, there's a couple of different ways we can find our volume. I mean, mathematically, you're really kind of doing the same thing, but I like to do it as basically the same way we found the precipitation for the unit hydrograph, the precipitation for our original hydrograph to begin with. So in that case, your volume is going to be equal to your 5 inches of runoff times the area that the runoff is going to be contributing from. And then all we have to do is convert that into feet. And so from that we get 833 acre feet. You could also do it by finding the unit volume. In other words, find the volume basically of your unit hydrograph and then scale that up. If we were to do that, did I just break? Okay, good. I don't know why that gets thrown off sometimes. So our unit, we'll call that volume U, 2,000 acres times 1 inch, and then convert it into feet. And then basically we times that by the 5 inches. Right, so pretty much we're doing the same thing. It's just a little bit of a different approach. Okay, that finishes up our example problem for today. I hope that was helpful. If you did find it helpful, feel free to leave a comment, or if you think this video would be helpful for others, we absolutely appreciate it every time someone hits that like button. Either way, we definitely appreciate you watching the video, helping out the channel, and we will see you next time. Thanks.